All right, let's just jump right in. Have you ever stopped to think about how your phone knows it's you instantly? Or how a self-driving car can spot a person on the street? Well, the magic behind all of that is a really powerful kind of AI called a convolutional neural network, or a CNN for short. And today, we're going to pull back the curtain and break down exactly how computers are learning to see.
So let's start with a really simple question, something we can all relate to. How in the world does a computer recognize a cat in a picture? I mean, for you and me, it's a piece of cake. We see the whiskers, the pointy ears, the fur, and our brain just goes, yep, that's a cat. But for a computer, it's a whole different ballgame.
See, when a computer looks at this photo, it doesn't see a cute, fluffy cat. Not at all. It sees what's shown here, a giant grid of numbers. That's it. Every single number just represents the color and brightness of one tiny pixel. So the real challenge for the AI is to somehow find the pattern of a cat hiding inside this massive ocean of numbers. It's an absolutely mind-boggling puzzle.
So, how do you even begin to solve a puzzle like that? Well, researchers did something brilliant. They looked at the best image processor we know of, the human brain. The big breakthrough came from basically copying how our own visual system works, a system that's been fine-tuned by millions of years of evolution.
And what's so cool is just how direct the parallel is. In our brains, we have these special areas in our visual cortex. You see them listed here as V1 and V2, and their whole job is to spot the basic stuff first. You know, simple edges, lines, curves. Only after that do other parts of the brain put those simple pieces together to see a whole object. And a CNN? It's built to do the exact same thing, just using layers of artificial neurons instead.
So you're probably asking, okay, how does a CNN actually do that? Well, it uses a very specific set of tools, or layers, and each one has a very specialized job. Let's break down the three most important parts of the CNN toolkit.
First up, we've got the star of the show, the convolutional layer. Now, I want you to think of this layer like a team of super specialized detectives. Each detective is given a magnifying glass, which we call a kernel, and is told to look for just one thing. Maybe one detective is only looking for vertical lines. Another is searching for sharp corners. A third is just trying to find a certain texture. These little kernels just slide over every single part of the image, looking for their one specific clue.
This diagram here shows one of those detectives in action perfectly. You see that little box, the kernel, as it moves across the image of Tweety? That's our detective's magnifying glass, searching for its one feature. And as it scans, it creates that new image over on the right, the feature map. That map is basically the detective's report. It's a map that lights up everywhere it found its clue. And a real CNN will have hundreds, sometimes thousands of these detectives, each one creating their own map for a totally different feature.
Okay, so now we have hundreds of these detailed maps. That's a ton of information, and the network could easily get bogged down. That's where the pooling layer steps in. Its job is super simple: clean things up. It looks at each feature map and shrinks it down, but it does so cleverly by keeping only the strongest, most important signals. It's kind of like taking a long, rambling report and boiling it down to just the key bullet points. This makes the whole system way faster and helps it focus on what really matters.
And the last tool in our kit is the activation function. Now, this one's a little more abstract, but it is absolutely critical. Put simply, this function acts like a gatekeeper. It decides that the information a detective found is important enough to get passed on to the next layer. But its most important job is adding something called nonlinearity. Without it, our network could only learn perfect straight-line patterns. But the real world is messy. It's full of curves and complex shapes. This little function is what lets the network learn those intricate real-world patterns that make up something like a cat's face.
All right, so now we have our toolkit, right? We have the convolutional layer to find the clues, the pooling layer to summarize them, and the activation function to handle complexity. So let's see how it all comes together to go from a jumble of pixels to an actual prediction.
It's all about building up layer by layer. The very first layers of the network, their job is just to find the most basic stuff: simple lines, corners, patches of color. Then, the next layers take those simple maps and learn how to combine them into slightly more complex shapes, like an eye or an ear or a nose, and the process just keeps going, with each layer building on what the last one found, until the final layers can recognize really complex things, like whole faces or paws. And then, at the very end, a layer called the fully connected layer looks at all this evidence and makes its best guess. Okay, I'm about 70% sure that this is Tweety.
So this incredible journey, from raw pixels all the way to a confident prediction, is how a CNN builds up an understanding of what it's seen. It's this beautiful pipeline that starts with nothing but numbers, uses layers to find simple patterns, combines those patterns into complex objects, and finally makes a call. It really is a beautiful hierarchical process.
Now, this technology didn't just pop into existence. It's actually the result of decades of research, and it's marked by a few really key moments that completely changed the game and kicked off the AI revolution we're living in today.
The story really begins back in 1989 with something called AlexNet. It was the first real CNN, and it was amazing at recognizing handwritten numbers, like for the post office. But then, the tech kind of stalled for a while, until 2012. In 2012, everything changed. A model called AlexNet just crushed the world's biggest computer vision contest, ImageNet. I mean, it wasn't just a little better, it was so much better that it stunned everyone and basically started a gold rush in AI. And since 2015, we've just seen this explosion of even more powerful designs that are constantly pushing the limits of what's possible.
In fact, that 2012 breakthrough led to what researchers call a Cambrian explosion of new CNNs, and this chart here gives you a sense of what they mean. Don't worry about reading every single name on there, just look at the shape of it. See how the field just branches out and explodes from that one point in 2012? You've got whole families of models like the Inception branch or the ResNet branch, all trying out different ideas for how to build deeper and smarter networks. It was a true design revolution.
So why does any of this tech jargon matter to you? Well, because this technology is literally everywhere now. It is the very core of self-driving cars that need to see the road. It's being used in hospitals to help doctors find tumors in X-rays with superhuman accuracy. It's what powers the Face ID on your phone and the object recognition in those stores with no cashiers. It's even used to help Siri and Alexa understand the sound of your voice. CNNs are, without a doubt, quietly changing our entire world.
And all of this brings us to one last, really big question. We know that CNNs can now see with superhuman accuracy in a lot of specific tasks. They can spot things better than we can. But do they actually understand what they're seeing? Or are they just incredibly sophisticated pattern matching machines that don't really get the context? Honestly, that's one of the biggest and most fascinating questions that AI researchers are tackling today.
Hey, if you enjoyed this deep dive into how computers see, do us a favor and subscribe to the channel for more explainers just like this one. Give this a like, it really helps us out, and definitely let us know down in the comments what complex topic you want us to break down for you next. Thanks so much for watching.